Okay. Let's start continuing the teaching voltage amplifiers, basically continuing the BJT voltage amplifiers. Right. Okay. So last time we reached to this page. We are trying to see what is the voltage amplifier and why we are using it. This is showing one example that we want to amplify a tiny receive signal from microphone, amplify it, and deliver it to a speaker, right? We tell that the microphone is similar to some voltage source that produce converts the audio waves into some electric signal, right? And then if you see here, the microphone also may have some output resistance, right? It's not a pure voltage source. It is like a Thevenin, so it also has some internal resistance. Then you will connect this to your, let's say, amplifier. You want to amplify the signal, right? To drive your speaker. And then the speaker itself is something like a resistive load, right? And you need to drive it. So ideally, every amplifier has some input resistance, as it's showing here. So the input is not infinitely large. It has some limited impedance. So initially, once you connect the microphone to this, you will see that there is some voltage divider from the generated voltage from the microphone to the input of the amplifier, right? Because of the limited input impedance of the amplifier. So the input impedance of the amplifiers is important, because if you see that if the Rin is too low, what will happen? So what will happen if the Rin is too low? The voltage of the microphone that's supposed to be at the input of the amplifier actually will drop because of this the resistive voltage divider. Because the microphone itself is not ideal, it has some internal resistance, right? So as the voltage amplifier, you prefer the input impedance to be what? to be high, right? So that you make sure that even in the presence of the the source resistance, still you can get more voltage at the input. On the other hand, the output has the similar situation. You can model the output side by let's say kind of voltage source again and time and output impedance, right? And then once you have the voltage source at the output and a series output impedance, and you are supposed to drive in some load, and again this voltage divider thing happens at the output side, right? So at the output side, what will happen if the output impedance of the amplifier is too big? If the output impedance of the amplifier, so the amplifier, you can model it as a voltage source, right? With some output impedance of it. What will happen if the output impedance of the amplifier is too large? The voltage delivered to the load basically will be less, right? Right. So ideally, you like the output impedance of the voltage amplifier to be smaller, right? So the ideal amplifier, you prefer the input impedance to be very high, but the output impedance to be very low. Okay. So now we know what is the importance of the input and output impedance. So practically in the circuits, we have, let's say, two-port uh, amplifier, let's say. To find the input impedance, basically, we assume the output is like not loaded, is opened. But for the output impedance, we are usually assume that the input is shorted. So this is just, we will see this in examples more. But let's start to find out what is the input impedance and output impedance of the common emitter device. So you remember once we have a common emitter, the input is basically at the base, the emitter is common, is the base ground, and the output is at the collector, right? And then we saw that you can model this transistor with this small signal model, right? There is a diode junction at the base emitter. You put the equivalent resistance at the biasing point, R pi. The R pi, do you remember what was the value of the R pi? 25 milli is basically, I tell this way, is VT, 25 millivolt, divided by the IC times the beta value of the device. So basically, the BJT device, everything is coming from this GM, in fact, and the GM is just IC over VT. And basically, this R pi is also, you can write it as the GM because it's inverse of the GM, but there is a beta factor if you want to memorize, right? So the small signal basically starts with this R pi and the GM. All of these things are depending on the bias current. And then there is some big resistance of the device, R out, usually very large resistor. And this is the load, we put it here, right? So from this equivalent model, you can easily tell that the input impedance, you put a test source here, right? Try to measure the IX to figure out what is the input impedance. Basically, is nothing than this input resistor, right? So you could easily tell, right? So in electronics, actually, this R pi is considered not a very big resistor. So you need to have some sense about the values and which one is very big, which one is slow. There is the ratio is important always. So R pi respectively is not very low, but is not very high, right? In electronic, we try to get more sense about the values and the ratio of the numbers. And how about the RO? The RO is the output impedance of the intrinsic device, which was because of the early effect in the DC curve, if you remember. So if you sweep VCE in the DC curve, you ideally like to have very constant current source, right? The constant current source. But in fact, if you change the VCE, if ideal current source, if you change the voltage across the collector emitter, it should not change the value, right? Because the current source, the current is not depending on the voltage across it, right? So the ideal current source, basically, you can tell that the impedance is basically infinity. Because if you apply some voltage across the current source, like V test, you cannot change the current, right? So the V over I, basically, the small signal, is infinity, right? I is not changing, is zero in AC, right? You are you're putting some AC voltage, but there is no AC current because this is always fixed at the DC value, for example, right? So ideal current source basically has very large output impedance. But in practice for the device, this curve IC is not very fixed over the VCE. It is kind of having some slope, but the slope is not too much. So basically, there is some resistance. It's not very ideal current source. There is some output resistance, and this output resistance is you can calculate by there was a voltage term called V early factor divided by IC again. So this resistor is a big resistor. What you need to know is this resistor, the output resistor is basically a big resistor. R pi is not too small, not too big. But RO considered the big resistor usually. And as you are seeing that is all the values of this RO, R pi, and GM all depends on this IC or the bias current. Right? So let's see how is the R out for this common emitter, basically. So again, you put this small signal model, right? Need to short the input. And then you need to basically put some test voltage here, right? And see what is the output current. And then this again will be easy because here you put a 0 volt short. So basically V pi is 0. If V pi is 0, this is not here, basically, right? And then what you are seeing only are out, right? So for the common emitter, basically the output impedance is big. Impedance is kind of R pi. R pi is not too big, not very small. Is it good for making amplifier as we wanted at the beginning from the impedance perspective, right? What is the problem with the common emitter as the amplifier? It is not that high. No, we want to be high, but the common emitter is not too high. Is R pi. R pi is mild. It's not too low, but it's not high. And how about the output impedance? Output impedance is very big, right? Because it's R out. R out is big, right? And we like to have the output impedance of a low output impedance. right? So it's not very well suited for making the voltage amplifier. So for the transistor, actually, we can look at it from the emitter side, right? We can assume that the input is at the base, the collector is the DC, so it means that AC ground in the small signal. And then let's see what is the impedance from the emitter side. So again, if you want to do so, you need to add the test voltage here and try to find the current, right? To see what is the impedance from the emitter. So this is easy to calculate again. So in this case, we are just assuming that the R out is very big. We didn't show it here, right? There is one R out here in the model. If you assume it too big, then doesn't need to put it. You can see why it is not assumed later. So what you are seeing here is, basically the impedance seen from the emitter basically is what? Is R pi divided by 1 plus beta, if you want to be accurate. And you remember the R pi was what? You remember what was beta VT, right? You need to actually memorize these values. This is not that difficult, but and then divide by 1 plus beta, basically 1 plus beta and beta basically are similar, right? Because beta is large enough, so you can tell that 1 plus beta is equal to beta. And then what we remains is VT over IC, right? And this is actually 1 over GM. Is it okay? So the impedance seen from the emitter basically in this case is 1 over GM. So you need to remember that 1 over GM is considered as a very low impedance, right? So now we have three impedances, right? One is RO, which is big impedance. The R pi is kind of mild impedance, not too big, but not too small. And there is this 1 over GM impedance, basically, which is considered the small value, small impedance. Sure. Okay. So you need to write the KVL KCL over here. One KCL over here is not that difficult, right? But intuitively, you can tell that actually this current of the device is IB, right? The current at the emitter is 1 plus beta times of it, right? So once the current is higher, basically the impedance is lower, intuitively, just intuitively. So for the BJT, actually, you can pretty easy actually move the impedances from the base to the emitter side because you already know that the current is scaling with this much, right? The current at the base and the current at the emitter always is this ratio. So the impedances at the base can be transferred to the emitter with this ratio. So you can write the equations to figure out how it is doing, right? Solving this circuit. But intuitively, you can tell that there is this resistor at the base, right? I want to move it to the emitter side because the current is 1 plus beta times, so the impedance should be 1 beta times less, right? So easily you can tell that the impedance is 1 R pi plus divided by 1 plus beta, right? So we are not going to write too much KVL KCL. We try to get this kind of techniques to quickly move the impedances and voltage sources from one port to the other port. But Now we need to remember that the RO is a big value so far, R pi is mild, but GM 1 over GM is low impedance, right? So this tells what? So if we have this kind of config for the amplifier in terms of the impedance, how is the output impedance? This is called common collector, right? Because the collector is common between the input and the output is AC ground. So this common collector, the output impedance is what? Is 1 over GM, right? 1 over GM. So this is how is this good for the output stage of the amplifiers? It is good, right? Because for the voltage amplifier, we like to have the low output impedance. So here we can see that maybe this kind of config is good to be at the output for the impedance level, right? So here is just a summary detailing these things. So the input from the base is R pi, not too big, not too small. From the collector, what we are seeing, these impedances are out, right? Which is a big impedance. And from the emitter side, we are seeing something around 1 over GM, which is low, maybe good for the output section. Then we little bit talk about the bias. So as you see, the bias is important because it's changing all of the parameters of the device, RO, R pi, and GM, right? So we need to figure out how to bias the circuit. So one way to bias is just directly apply a DC voltage to the base because we need the base emitter junction to be forward bias, right? And then the base collector to be negative reverse bias. So to make this turn on, basically you can have some voltage source at the base, right? And try to turn on the base emitter diode. And then you have this VCC to make this voltage higher and some load, right? Is that way is good to use for biasing the BJT device? Do you have any idea if this way of biasing is good or not? You put a DC voltage here, let's say. Let's say this is a DC voltage just directly is trying to bias the diode. What is the problem with it? First of all, this voltage source should be how much? It should be something around 0.7, right? But what is the problem with this? So just think about the bias currents now. Once you put this voltage source, what is the current of the device? Yes. Which impedance is zero? Here is zero. You mean the impedance is zero, the current should be higher, right? This is a voltage source, right? You're having a voltage source basically connected to a from the base perspective is like this, right? One diode. What is this current? It's not very well defined, right? It's not very well defined. It's because why? Because the diode current is basically IS exponential relation, right? So it can easily goes very extensively gets higher, right? It's not very well controlled. If you change the VBE, the current may change exponentially too fast, right? So you do not have that much of well control over the IB and again IC, because IC also is beta times of IB, right? So this is not a good scheme, right? How we can confine the current of the base, right? You can put some resistor in the series with the diode so that you be able to fix the base current basically, right? So for this, let's say this type of device, this type of bias, we have the base resistor, right? What is the base current? It's already written here, right? You need to just write 1 kVL or kVL from here to here, right? VCC minus R by RB times IB minus VBE is 0, right? VB is almost fixed, 0.7 volt, right? You have the VCC value, your supply voltage, for example, and this RB define how much current is going in. And how about the output collector current? Basically, we want to find the collector current. It's basically beta times of the IB, right? So the collector current is just beta times of the IB. Is that clear? So is there any problem with this type of bias? What is the problem with this bias? You can tell from these parameters show up in the equation, basically. What parameter is, yes? What are the parameters that showing? So VCC is output from the outside is under our control. Is still fine. What else? The beta is some parameter in the transistor which is very dependent on the temperature, device to device, is not that constant that you can perfectly tell that the beta is this much. And varies by device model and device type and the temperature, everything, right? So this beta is something that we do not want to make inside our biasing. So we don't like to have it because it's not under our own control. What else? What else is not under our control? Each the base resistor we put it, right? We adjust the value, we put it ourselves. What else is not our under our control? The VBE, right? So actually everything depends on the device is not in our control, right? It is given to you. You have the device, you don't have that much of control. But the VBE in certain case uh, is a little bit better defined. You can tell that the VBE on is something around 0.7, but it still varies between different device sizes or different device types. Like if you use the silicon, maybe it's close to 0.7, but if you change the device with something like germanium, it may change it to be going to be smaller or something, right? But one more actually important parameter that is not show up directly here is the temperature. So both the beta and VBE change very harshly over the temperature. So the VBE or turn on voltage of the device is changed with the temperature like with this slope, negative 2 millivolt per degree C, right? Every 1 degree that increment in the temperature actually reduce the VBE value by negative 2 millivolt. So what will happen if we In fact, what will happen if we, let's say the temperature varies from, let's say 0 degrees C to 100 degrees C. So the VBE, right? The VBE, the turn on voltage of the diode, basically changes with the temperature. The slope is like negative 2 millivolt per degree C. I am telling that, let's say, if the temperature changes in your circuit from 0 degree to 100 degree, what will happen? It's gonna be lower. How much? Assuming this is slope. We changed the temperature, how much? Each degree. Now we are, let's say, change the temperature of the circuit like 100. Yes. Minus 200 millivolt, right? Will change. This is the change. 200 millivolt means zero point 0.2 volt, right? Means that if you start with 0.7 volt initially, now will be what? Right? So it means that this VBE actually is changing, right? And this VBE changed so much. The beta also changed. We are not seeing here. The beta also changed. The beta will increase also. So in fact, what will happen is once you go from low to high, what is happening? This term will be less. The bias should be higher, right? VCC, let's say, is constant. Base resistor is constant, but this VBE is reducing, right? The collector current will be higher. But it's not only this. This beta is even more harsh than this. So overall, the transistor's current will extensively increase, right? So this bias is not good because uh, it doesn't have any control over the temperature, basically. So why the temperature actually goes up? Why the temperature goes up in the circuit? Yes. There are two things. One, the environment temperature, right? The environment temperature eventually changes the temperature of everything, right? So if you go outside, the temperature is higher, your circuit is gonna work at a higher temperature. But the other source of the temperature is basically the amount of power wasted inside the device from the voltage and the current of the device, basically, right? So for this device, let's say this transistor, if you have, let's say, this VC, let's say the collector voltage, let's say is 10 volt, and then you bias the transistor by zero point 0.1 amp, right? How much power actually is wasted inside the device? But I just ignored the top circuit. I just thinking about the device, right? Let's say the VCE, the collector emitter voltage is 10 volt, and then there is a current passing through the device, which the value is zero point 0.1 amp. What is the power dissipated inside the device? How much? One, right? Basically, the power of each component is V times I, right? Voltage is 10 volt, and the current is zero point 0.1 amp, so basically is 1 watt. 1 watt is dissipated inside the device. And this dissipation actually increased the temperature of the internal circuit, right? So you turn on the circuit. Initially, let's say we call it the junction temperature because it's a semiconductor with some junctions inside, right? Junction diodes. So you turn on the circuit. Initially, the circuit is cool, right? Initially, you start with 10 volt and 0.1 amp, and you are dissipating 1 watt inside. What will happen? You are burning some power inside the device, right? And then the junction temperature of the device, because of this bias, is increasing, right? Because you are wasting some power inside, right? And then what will happen? The temperature goes up. What will happen? The temperature goes up. This VBE drops, right? The beta will increase, right? And then this IC will be what? The IC increases, right? It's getting higher, right? That's true. And this uh, loop will continue. It will be burned, right? If you do not control it very well, the device and the power dissipated into it, it keeps with a positive feedback, increase the current until the device burn. And this situation, we call it thermal runaway for the device. So if everything is not well managed, then there is chance the device go to the thermal runaway. Right? So the bias then is important. So yeah, one more robust way to do the bias basically is using this circuit for the BJTs usually. First of all, you use some voltage divider to make the voltage like the base voltage for you, right? You can assume that the base current is not too weak, so basically this Vx is what? This Vx. So if we assume that the base current is not too large, you can assume it like kind of like opens right at the moment. And then the Vx is what? I try to calculate the current for this. Right? It's just a voltage divider, right? R2 plus R1 times the VCC. This is the Vx, right? And then what is the current of the device? I mean, the base current, how you can find it? Yes, there is some like equivalence circuit for this. The Vx is like this, right? This value, the R Thevenin is basically R1 parallel to R2, right? And then you have this device, there is some RE, right? So you need to just write 1 kVl inside here, right? So what will remain, what will be the final value? For the IBIS or IC. So you just, for simplicity now, you assume that there is this R Thevenin is too small. Basically, you are putting the base with this voltage Vx. Or let's say assuming that IB is much less, so that the R Thevenin times IB is nothing almost. So can you repeat? Yeah, plus, right? Plus, I write VBE. Yeah. No, you just come from here to here, right? Yeah. R emitter times what? I emitter, right? Equal to 0. So what is the I emitter then? So I assume now the R Thevenin is small enough so that we can just ignore it at the moment. So what will happen is the IE, the emitter current is what? Is basically Vx minus VBE, right? Divide by RE, right? Along with it. So how about the IC? This is the emitter current. How about the IC? We actually want the IC, right? So basically from here you can see that the IC is just sum of, I mean the emitter current is the sum of the IC and IB, right? They are combining into the emitter, right? We know that the IB is not too big, so you can basically roughly tell that the IC is pretty much similar to IE. But if you want to really become accurate, IC is beta over 1 plus beta times IE, right? But from here, you can tell that this IB is combining with IC, making the IE, right? But the IB is usually much less than IC, so basically IE and IC are pretty much similar, right? But if you want to be accurate, it's like this, right? IC is almost similar to IE for us. So we can tell that then this IE we calculate basically is IC. So how is this time? What are the parameters that is under our control or not under our control in terms of this biasing? Still VB is not under control. Any other parameter that you think is not under our control? So I'm asking that this biasing circuit for the BJT, we come up with this IC value. The IC is equal to Vx, which is the voltage divider of these two resistors, minus VBE divided by RE. This is the collector current. I'm asking that which parameters in this equation is our own control or not. We want to control the collector current. What of these parameters are under our control and which one are not? Vx, we can adjust it, right? You are the designer. You can adjust the R1 and R2 values to make the Vx, because the Vx is coming from this voltage divider between R1 and R2 and the VCC. So as the designer, you have the control of the VCC, R1, R2, right? The RE is under your control, right? You put this value. So in this case, only the VB is basically is not under your control, right? Isn't it better than the previous one? The previous one, there was a beta here, right? So at least it's not depending on the beta. So no matter what device you put, you can tell roughly without knowing the beta, this is the current of the IC. So this design is a better and more robust design, right, for the bias. How about the temperature variation? Right? True. The, if you change the temperature, what will happen is, so let's say we change the temperature from 0 to 100 degrees. The VB starts from, let's say, 0.7 volt to what? To 0.5 volt, for example, right? So how the IC will change? It gets higher. But the good thing is that how much gets higher, let's say. So once the VBE, so let's give some example. Let's say the Vx is 1 volt, right? Let's assume that the Vx is 1 volt, and then VBE starts from 0.7 volt, right? And the RE was something like 1K, for example. How much is this current, roughly? How much is the collector current? Right? 0.3 milliamp, right? And what will happen if you increase the temperature 100 degrees more? Right? So 1 volt is still fixed. This is 0.5 and this is 1K. It will be 0.5 milliamp, right? So the first of all, it's not increased very extensively like the exponential, but still the variation is too much, right? It's almost double, basically, right? 50% change or no, 100% change, right? So this is not yet good enough for us. So how we can reduce this variation? There is the variation. So far, we cannot do anything more, but still you can do something to reduce the variation. Now you are seeing the variation is kind of around 100%. But it's not like the bad way that the thermal runaway happens because it's not like very like exponential. So what you need to do is to read. No, this is is the DC. That RPi and RO for the AC model, right? So the DC, we just care about the turn on voltage and the resistance value over here. So in this equation that we have, actually, these two, what parameter if we change, we can reduce the variation. The RA is not doing anything, basically, in terms of the variation. It changed the absolute value. So you can try, right? If you put 2K, just everything scales half, right? So the change ratio is not changing, right? So you want to make some circuit that the variation, the bias is not too much over the temperature. What else you can change? Exactly. That's true, right? So in fact, in this equation, you only the other control knob you have is this 1 volt, right? If you increase the 1 volt high enough, then because this current basically is this voltage minus this variable voltage, basically, right? If this voltage is high, then if you subtract something from it, it doesn't change the final value that much, right? So just very harsh example. If I put the Vx like 100 volt, right? Uh, If I put this Vx very big, like 100 volt, then the VB is not changing, right? It's only 0.7 volt. And you put some RE, you get some IC value, right? And then if this VB even changed to 0, you are comparing this voltage with 100 volt, right? So the current is not going to be changed too much. Is it clear? So practically, we try to bias this Vx actually not less than 2 volt to minimize the variation or make it reasonably fine. So if we put this 2 volt in this example, what will happen is, let's say 2 minus zero point 0.7, the current, let's say initially is 1.3 milliamp, right? And then becomes what? 1.5 milliamp at the high temp, right? You see the variation is not that big now. So basically in the design of the BJT, we try to use this kind of a structure for the bias because it's not dependent on the beta. And also the variation over the temperature, you can control it by at least put this Vx something more than 2 volt. This is the rule of thumb. There is other biasing circuits like this one. Can you try to find the IC for this circuit?
So here I see is across the resistor RC or
IC is the collector current, but also pass through the RC, right? Some part of it pass to the IC, RC, right? So there is a base current and a collector current. So the sum of them, sum of these two basically is passing through RC. So you need to write the KVL basically from top to comes here and go to here. So you can write the equations, but I don't want to spend more time on the bias so far. But this still can be adjusted if you make this parameter to work in a proper region. But still you are seeing that this is a little bit depending on the beta. If you do these conditions, there is less sensitive to beta. There it is saying that. So it's also possible to make this work for you. There is one advantage over here that is mentioned here, which is actually you are in this bias, you are always make sure that this voltage of the collector, right, is larger than the base. So it means that this diode over here is always reverse bias. So this is good in that perspective that the device is always in the active region. Because in the active region, we need that this one is to be forward bias, the other one to be reverse bias, right? So this also works. The reason I'm not going through it because most likely people use this way. And for the PNP is pretty much similar, so we just skip this for now. Okay, then again we go back to the small signal to find the amplifier's performance. So you remember we start with the common emitter, we saw the input impedance and output impedance, right? And now it's time to find the voltage gain, right? So this is the small signal model of the transistor in the common emitter format, right? So we want to calculate the gain, voltage gain. Voltage gain means what? The ratio of the output voltage, small signal, to the input voltage, right? The circuit was like this. You had the VCC, RC, and then let's say you have this, you have biased it with a bad way, like with the bias, DC bias, plus you have an AC source. This is not the way we bias, right? We know that. But this small signal model for this becomes like this, right? So for the small signal model, what you do is you short circuit their DC voltage. Do you remember? Because those voltage sources are constant. They are not going to vary, right? So for the constant variables or source, we just assume they are zero because we are trying to find the the voltage once you apply the AC, right? So VCC is zero, so that you are seeing that in the small signal model, basically, or the AC model, we are assuming that the RC is connected to zero from one side, right? And here we have the V in source, right? And then we want to figure out what is the V out to the V in. So for this one is pretty easy, right? How pretty easy? So once you apply a voltage at the input, basically the V pi, which is over here also, is just V in, right? So you already know how is the output current, right? Is easy, right? So just the output current is just GM times the V in. And this output current is just passing through your resistor, right? So if you just write the case or KVL from here, this loop, basically you can find this voltage, right? And the gain, in fact, will be just the voltage gain, basically, is just this value, right? V out over V in will be negative GM RC, right? GM times V in basically makes this current. This current is passing through this resistor, makes this V out for you, right? Since the direction of the current is this direction and this voltage, then there is a negative sign, right? Is that clear? I guess don't need even to write any equation. Basically, you have the V in across the input. Basically, the V in is the V pi. So basically, you know this current GMV V in. This GMV in, basically, all the current is passing through this resistor, right? The current passing through the resistor means that this voltage is what? Here is 0 volt. Here you have the current of GMV in. What is this voltage? 0 V out, right? Just a voltage across the resistor once you know the current. And then it will be like this, right? So from this equation, what you figure out is what? How to increase the gain. We usually want to have more gain. How we can? Which parameters are under our control? The RC is under control, right? What else? Is GM under control? Isn't it? What is the GM? What is the GM value? How calculate the GM is, yes, right? This IC over VT. Is this under control or not? If you want to increase the gain of the amplifier,
Yes.
right? How?
I see with that.
Right? You can control the IC. So increasing the IC, basically you are increasing the GM, right? And then with the RC together, you can control, right? So here is just putting the GM value here, right? It's describing the same thing. And you see this IC times RC basic is the DC voltage across the resistor. Is that clear? Do you see this? The IC-RC basically is the DC voltage of the resistor, this resistor. Can this DC voltage be infinity? There is always a limit, right? What is the maximum value for this DC voltage across the resistor? Is VCC, but if you want to be a little bit more accurate, because this cannot be go to zero, right? This voltage needs to be at least some value. So here is assuming that there is some VBE needed, at least, like 0.7 volt, to make sure that the device is in active region, right? Otherwise, the device is not inactive and all of these things are not working, right? So you are saying that the gain basically is limited to this VCC at the end. If you want to make the transistor at the active region, right? So there is a limit then. So here is showing just demonstrating the if this DC voltage is higher and you have this 2 millivolt input peak to peak AC signal, the output, let's say, has some gain, right? The output peak to peak is 77 millivolt, for example. If you change the RC value or the current or GM so that this DC comes down, means the gain is higher, right? How this DC voltage drops more? Basically, if this goes lower, means that the DC across the resistor is higher. So the gain is higher, right? We expect the gain is basically same as the voltage across this resistor. So what you are seeing is the DC voltage of this node is lower, but the amplitude of the output is higher, means the gain is higher. This is showing that, right? And again, we already had seen that the input impedance of this common emitter is just R pi, the input impedance. The output impedance. So in the initial circuit, we had also the R out, if you remember. But now we put the RC in parallel with the R out. Why now we are writing here that the skipping the R out, right? The R out is a big resistor usually, right? So comparing to our own added resistor, basically R out is bigger. So in the parallel of two things most probably is like RC, right? Just you can skip it. So here is showing that you want to increase the gain, then this is showing the trade-offs between the different parameters. So you want to increase the input impedance, you need to reduce the GM. But on the other hand, you want to have higher gain. right? You need to increase the GM, right? So all of these things are in a trade-off. You cannot get all of the aspects of the good amplifier from the common emitter, right? So here is trying to add this R out of the device into account. So the total impedance at the output, the gain will be like this. Before was only RC, now RC is in parallel with RO, right? Nothing changed. So in fact, here is trying to say, what if there is another limit for the gain, basically, right? So for the voltage gain, we told that the gain is GMRC, right? But now, if you are considering the R out, it will be GMRC in parallel with R out. So in fact, if you want to get the highest gain, basically, you need to increase the RC to infinity, right? Just skipping that. Yeah. What is the question?
No.
I mean, if you just ignore the saturation problem that we mentioned before, at least in this small signal domain, if you want to increase the gain, it's just saying that you need to increase the RC. But if you increase the RC too big, you will be limited to what? In fact, the GMRO, right? So this is the absolute maximum gain of the device, basically. So previously we discussed once we increase the RC, there is a limit because of the bias and the saturation point in the previous slides. But now I just skip that. I am assuming there is no saturation problem. I just try to get highest gain. So from here, I can tell that we need to increase this resistance value, but if you increase it infinity, then you will come up, the voltage gain will be just GMRO. Everything just depends on the device. And then again, you can go back and see that this RO, the value is basically the V early divided by the IC. The GM is what? The GM value is IC over VT, correct, right? Then this absolute intrinsic gain is basically is the V early over VT, right? The V early value for BJT is in the range of 100 volts. VT is how much? Right? 25 millivolt, right? Then what would be the expected highest gain for this? For
Kilo.
4 kilo, I guess, right? Yes, the single stage common emitter very ideally can reach this much of very high gain, right? 4,000 times. Yes,
Can you explain again?
yes. So initially we didn't include the RC here, right? You remember the R out. Initially we start only with RC, and then we come up that the gain is GMRC, right? If you to increase the voltage gain, actually this equation says that you can increase the RC to infinity, right? And you should get infinity gain, basically, right? If you just using this equation. But in practice, we are seeing that if there is some other output resistor to the device, I mean the device itself has some output resistance, is RO. This RO is part of the device, but initially we skip it. Now, if you increase the RC value too much, then this RO becomes important because the final gain, if the RO is here, basically is RC in parallel with the RO, right? And once you increase the RC to infinity, then basically what remains is just RO, right? The maximum resistance that can left over here is basically the RO. You cannot really make it infinity. So here we have some other definition. So for at least for the single transistor is easy, right? The ratio of the input current to the output current is beta for a single device. That's just saying that. So we are trying to see what would be the characteristic of the amplifier, like the emitter, common emitter, once it has some resistor at the emitter side. So why do we put this RE here? Do you have any idea? Let's say we want to make an amplifier, right? The input is the base, the output is the collector, but we put this resistor at the emitter side. Why do we need to put this RE to increase what? No, I mean just the it will increase, but uh, it can be because of the level shift that you are saying, that you are saying, right? Means that the DC level of the V in will increase or change. But what is the purpose of having this RE from other perspectives? From the bias point?
To have a
What was?
negative feedback, Milad.
So can you repeat?
To have a negative feedback.
Yes, no, just from the bias perspective that we thought initially. This RE helps for the bias, right? Do you remember? In the bias circuit, we use this kind of structure, right? So sometimes we need to have this for the bias, this RE. Yes, although it will generate a negative feedback, but now I just try to go back to our own knowledge, right? So the initial bias circuit that was working good was something like this. So it has this R emitter, right? This was less sensitive to temperature variation and better performance, right? So let's try to find out what is the voltage gain for this circuit then, because this is not going to be grounded, right? So if you write the equations and derive, you will come up that the gain would be like this. So initially the gain was GM-RC, right? Now there is a factor degraded. The factor is 1 plus GM times RE, right? This is the reason that we called it emitter degeneration, because it is basically reduced the gain, right? The original gain was like this if here was ground. Now, once you added this RE, basically the gain will drop by this amount of the factor. So is it the better way to calculate this thing easier? It is possible. So do you remember I was saying that the base and emitter, they have some relation from the impedance level. The impedance thing from the emitter was 1 over beta times less, right? Because the current was 1 beta times higher. Do you remember this? Comparing to the base. The base, the current is low, the impedances are big. The emitter, the impedances are low because the currents are higher. The ratio is between the base and emitter is 1 plus beta, or always lie, right? In fact, you can just skip this part of the circuit and try to move whole thing like from the emitter perspective, right? If you move everything to the emitter, basically what you are having basically will be like this. You have the R pi, but it will be divided by 1 plus beta. And then you have this RE, and you have the source, right? And then what would be this current? This is the V in. The emitter current would be your V in, right? This value, I just write it a little bit simplified, can be written as 1 over GM basically, right? Why? Because R pi was initially beta times 1 over GM, right? But we are shifting this R pi to the emitter side, so we are dividing it by 1 plus beta. And 1 plus beta is almost similar to beta, right? So basically you can cancel this. So this resistor R pi from the emitter side is almost 1 over GM, right? And then IE is what then? In this case is RE V in divided by R in plus 1 over GM, right? The series of the resistors. Is that clear? Right? I'm trying to not writing always the KVL KCL's very tough equations, right? I just transfer from input to some side, and then using these transformations, easy rules, we can directly reach to the final. So basically now we can calculate IE easily, right? Is the series of the two resistors, basically, right? The value of this one is 1 over GM, the other one is RE, right? So basically the emitter current is V in over this. And also we know that the emitter current basically is pretty much similar to the collector current, right? You have the emitter current, so this current basically is passing here because IC basically is pretty much similar to IE. Is that clear? So in order to find V out, basically you just need to multiply this current to the RC, right? If you multiply this to RC, it gives you the V out. There is a negative sign because of the direction of the currents. And then the gain would be this, right? The gain would be this. This is the other way of writing the same thing on the top. So what you need to remember from this basically is that the gain comparing to the original common emitter without any resistor, RE, is degraded by a factor of 1 plus GMRE, right? That's why we call it the degeneration emitter to this resistor. So from here, actually, there is some other properties from this. In fact, this degeneration, though reduce the gain, but it kind of make the gain insensitive to GM. It's how it can actually, if you are assuming that the GMRE is larger than 1 enough, right? Then you can simplify this gain to become like GMRE because we skip 1 plus 1 because GMRE is big enough, and then GMRC. And then the gain would be just negative like RC over RE. So basically it decouples the gain from the GM, right? So since this RC and RE are just the passive resistors, right? The gain is pretty stable and the gain is pretty well defined and is also not is very linear. The GM basically is from a device, right? Is nonlinear. Nonlinear means what? Once you are changing the input too big, because now we are just talking about the small signal, meaning that the input variations are pretty small, everything is small. But what if you increase the amplitude, then uh, then everything is start changing because the operation point, the DC currents are changing once everything gets very big. And then this GM is not constant. GM is also changing, everything changing, and then this circuit will be very nonlinear, right? If you want to have a good linearity, basically, we will talk it later. This could help a lot. So here is giving some examples. So if I give you this example for your exam, how do you solve it? Here is the V out, here is the V in to find the small signal gain, for example, from V in to V out. First of all, we need to find the DC currents of each circuit, right? Let's say there is some IC1, for this one is IC2, some bias. Then what do you do? What what is the next step? Need to find the AC, AC small signal, right? Right? You need to find the small signal models, right? Zeros the VCCs, open the current sources, right? Like that, right? So you just make it here 0, here 0. What else? You put this equivalent small signal models, right? It becomes some like a huge circuit at the end, what you see. But it's not that much necessary always to do so, right? You can you can basically quickly simplify it. What is here is trying is just initially you are seeing that this circuit is basically a common emitter with some degeneration emitter, right? And then there is something here. So from here, you need to find basically what impedance is this thing, right? This thing is what? This thing is just a simple transistor at the input. Even if you imagine the small signal model, you can see just the what you are seeing is just the R pi from this. right? You can imagine basically for the simple things, right? The model is like this, both sides ground. You are just seeing from this side of the base. Basically, you are just seeing the R pi, right? The other side is nothing to do with this circuit, basically. So, in fact, you put this R pi just in parallel with RE, right? What else? As I mentioned, you can actually transfer V in to the emitter side, right? If you transfer the V into the emitter side, what will happen is the emitter current would be V in divided by series of G 1 over GM because there is one R pi moved to here, right? Plus what? Plus what else at the emitter, right? RE in parallel to R pi 2, right? This will be the IE, basically the emitter current. And this emitter current is passing through the RC. You just multiply it by RC. Basically, it gives you the gain. There is a negative sign. Don't forget it, right? So this is how you generate it. You don't need to really uh, draw all the small signal circuit. We can simplify it quickly, right? This is another example, right? This time there is some transistor at the output, right? From the output side, basically this transistor, what you are seeing is basically R pi 2. So you put it at the small signal model, right? What will change is basically from the emitter is just 1 over GM1 plus RE at the denominator, but the collector and resistor has changed. Now is RC in parallel with R pi 2, right? So now we consider the gain. Now we want to see how is the input impedance of this section. I mean, once we added this RE. Initially, if you had this just a common emitter with a grounded emitter, what you were seeing at the base was what? Do you remember? Like a common emitter with the grounded emitter. What is the impedance at the base? We don't want to draw the small signal. We just try to get it. There is no resistor, but I just want to see what is the impedance if you put the small signal model of this. Only R pi, right? I mean, doesn't need to plot everything and every time, right? But now what we are trying to find is what is the impedance when we have this RE, right? So we know that what we know is that you remember we transferred the base impedance to the emitter. But how we did it, you remember? Once we go from the base to the emitter, right? On the other hand, we want to actually transfer the emitter impedance to the base because we are going to see the impedance from the base. Now what we should do is similar, right? The emitter current is beta times higher. The impedance is smaller. If you move it to base current is smaller. So the impedance is higher, right? So in fact, if you want to transfer this emitter resistor somehow to the base side, what you need to do is basically you put this R pi from the base and then transfer the RE to the base, basically, but you need to multiply it by 1 plus beta. because the base current is less. So you expect that base resistance is higher. So what you will have basically, the input impedance would be R pi plus this part of the resistor, right? Is it good or bad? Is it good? It is good, right? The input impedance will like to be higher, right? For the voltage amplifiers, we like to have a better, higher impedance. So one way to increase the input impedance basically is using this kind of emitter degeneration, right? For the impedance is good, but for the gain is how? The gain will be less, the gain will reduce. So it solves the impedance problem, but it is the gain also will be less.
Why do we care about the?
So it comes back to the initial problem. The initial problem, you need to design an amplifier. You remember you had the microphone, you model the microphone with some voltage source, but it has some limited output impedance, right? There is a voltage divider between the impedance of the source and the amplifier, right?
Yes.
If the amplifier impedance is low, then most of the generated voltage from the source actually is killed between these two internal resistor and input impedance, right? So you don't want to lose the voltage from the input to the input of the next stage. It matters the power, but now we are just focusing on the voltage. Sometimes we like to basically increase the maximum power transfer. But now we are actually thinking about the voltage transfer. If the power transfer, then you need to actually adjust this resistance value to become matched to their source value, to maximum power transfer, right? That the circuit you remember, there is a maximum power transfer theorem, right? But in this case, we are just caring about the voltage. So for the voltage, we don't like to waste the voltage inside the voltage dividers between the impedances, right? So for the amplifiers, we prefer to have a higher input impedance. So we are now seeing the output impedance once we have this RE, actually. So the is it the output impedance? Yeah. So the output impedance basically is only RC in this case, since we don't have any, we short the input, basically V pi is 0, so this guy is not here. So whatever left is just RC. Okay, let's see. These are not already discussed, basically. Okay, we need to also consider some more cases, a little bit more, once we have the base resistor, a little bit more general. So we studied this common emitter without emitter degeneration, with the emitter degeneration, and now we are adding this R base. So what will happen? How we can calculate the gain for this case? Now the V in is here. Before V in was here, right? You have any idea? how to calculate this gain. So we know how to calculate the gain from this A node to the output, right? But now we have this R base. What we need to calculate basically is first how the V in reached to the VA. If we know how the V in reached to VA, then from VA to V out we know, right? So in order to find the VA, right? So what is the solution? But how is the IB? I mean the AC. We are talking about the AC. The, I mean you need to find the base AC current, not the DC. We are just talking about the AC now. There is, of course, there is ice, some DC current, some DC current to the base. We are not showing now, right? We want to find the VA basically. If we find the VA, then we know how to calculate it, right? The gain. We know the V out to the VA basically is the common emitter with the emitted degeneration. You can calculate it by this times RC, right? But how about from V in to VA? You need basically to find the IB, as you mentioned, to subtract it. But to find the IB, basically, you need to find what? The impedance of the other part, right? You have this V in, you have the R base, you have some box, right? You don't know what it is. You want to find this value here, the voltage over here, VA. How you can find this, basically, let's say IB. Basically, you need to find the impedance, right? So this box that you don't know, it has some impedance to ground, right? So we model this box with input impedance of the box first, right? Again, the input output impedance are important because of this, because they are each box basically is loading some other thing. This is the loading effect, right? So what is the impedance of this box basically from the A point, basically from the A point? Is this right? R pi plus you transfer the R emitter to the base, right? Is this value, right? From the base side, basically what you are seeing is this, right? And then now it is easy, right? You can just calculate the voltage divider between these three resistors, right? So the VA is nothing, just you just do the calculation for this voltage divider, and then once you find it, then you put it to here, right? It's not difficult, right? Then you can rewrite everything, and finally reach to this formula. I do not derive it like this, right? It is just describing the same thing. So he's giving some examples. So let's say this circuit initially is this. For example, they try to bias the device using some current source. How we solve this? If I give this in the exam, for example, we want to find the V out to V in, the gain, voltage gain. Yes, so we find the first we need to find the bias of each transistor. What is the bias of the Q1? The bias current. What is the current of the Q1,
Um,
right? Yes, I1, right? So once you find the R I1, then you can calculate R pi, R out, GM, everything, right? And then you try to figure out the small signal model, right? AC model, basically. You remove this, you short circuit the voltage source. How about the cap? The cap, actually, we are trying to model this circuit for the AC signals, right? For the AC signal, the cap becomes what? If the cap value is big enough, you can tell that the cap impedance is short. Yes, right? At this moment, we don't care about you. We usually, let's say, design this the cap to be large enough so that for AC signals, the cap impedance is small. So, in fact, the circuit will be like this, right? We should be shorted. R2 is basically to the ground, R1 also to the ground, right? These two basically are shorted together, right? What is the problem with this? Is that okay? Basically, our C1 is short, right? C1 is short means that here is ground, also here is ground, so you can just separate it easily, right? And then the gain again is not that big deal. Basically, you have this R2 as the emitter, you have the base resistor, and then the equivalent collector resistor is these two in parallel, right? So here is trying to figure out the output impedance of this circuit. So initially we ignored this RO of the device, right? If we ignore it, it's gonna be infinity. But if you have it, in some of the cases, you need to really consider this, right? When you need to consider this, right? Initially we will skip this. We were skipping this,
see,
right? Once the RC is very big, actually, then you cannot tell that everything is infinity. So there should be something confined. So then the RO need to be there, right? To be more accurate. It's always the ratio between the impedances and the voltage and everything, right? Everything is the ratio. So for this one, you need to really write the KVL KCL to figure out the value. There is not that straightforward way, but you can, after a while, figure out the rule to find this output impedance. So basically, what you are seeing is that this equation is important at the end, is that normally if here was 0, basically you just see the R out. If the emitter didn't have the degeneration. But with the degeneration, basically the R out will increase. The R out will be increased by this equation, basically. So there is a increment in the R out with this boost, I mean this factor, 1 plus GM times RE in parallel with RPi. So we will return it back later on. Is it good or bad that the R out is increasing? Is the increment is also too high? It is considered is not a good thing for the voltage amplifiers, right? Because we prefer the voltage amplifier to have the very small output impedance. This is not good, as the voltage amplifier is not good. But how about if you really consider the output as the current source? Sometimes we care about use the transistor as the current source. The, the current source, the output impedance is how much? Ideally. For the current source, right?
For the current source?
Yes. The ideal current source, what is the output impedance? How is it?
Did not get the question.
I'm saying that if you have a current source, what is the output impedance of the current source? So in order to find the output impedance, you need to put some test voltage source or something, right?
Infinity?
It's infinity, right? It is not changing. The current is not changing once you change the voltage. V over I, basically, V over I, right? I is not changing. It's zero, right? So it's infinity, right? So after having this degeneration, basically, the output impedance is increasing, right? So then what will remain is basically kind of a better current source, right? Though it's not good for the voltage amplifier. Voltage amplifier, we prefer to have the smaller output impedance, right? But sometimes you are going to use this device as the current source, and the current source, you prefer the output impedance to be higher, right? So originally for the voltage amplifier, this is not good. But if you need to use it somewhere for the current source, then it's good, right? So this is just what I wanted to say. So here is trying to say what would be the limit of this R out once the RE is too big or R pi is too big, like this, comparing to RE, which can be derived easily from the original thing. So we will come back to this later, maybe. So here is trying to describe by inspection how the R out is. I don't know how it is saying. Oh, it's just showing how the capacitor is shorted and things. Okay. So here is showing the degeneration by another transistor, for example. What is the R out of this circuit? Right? Basically, it is trying to say that the first section is just nothing than one R out, right? It is just simplifying. Let's say the AC signal, AC a small signal model for Q2. Here you just put it short circuit at the base, and then from the collector perspective is only RO2, right? It just remain one RO2 at the emitter of the top one, right? And then again, it goes back to the same thing we saw before here, right here. In fact, the RE is only RO1 of the other one. RO2 actually. RE is RO2. And then we know that the R out in this case will be what? The RO1 times GM RE parallel with R pi 1, basically, plus 1, right? But now RE is basically RO2, right? Yes.
Can you go through the examples step by step?
For this,
Yeah.
sure. So let's say you are asked to find the R out of this config, right? Initially, right? First of all, you need to make the small signal model. So you short this bias voltage source, right? So for the Q2, the base will be short, emitter short, this short, right? And this Q2 basically is connected to the Q1. But from the Q2, what will remain basically is only RO2, right? You can see that there is RO2 here. R pi basically is shorted internally, right? I'm not going to plot every time the small signal model expands, right? You can imagine there is R pi, right? But the R pi is shorted to both sides, right? So there is no V pi. V pi is 0, right? So you can do it, but it doesn't need to. This is the small signal, right? This is the base. This is the collector, right? The base is short. This R pi is gone, right? There is no V pi, so this parent source also is not here. What remain is just RO2, right? You just put it here. And again, you have this circuit, which is basically there is RO1 here, there is R pi over here, right? And then once we had already solved that for this kind of emitter degenerated thing, the output impedance can be calculated by this. If you do not remember this, you need to drive everything by yourself. But these things since will be repeated more, so you need to somehow memorize it. It's better to memorize it. Otherwise, you need to do the KVL KCL for this. So now the case will be like this. You have this RO2 as the emitter. You know the final output impedance would be in general like this formula. Our emitter is the emitter resistance, equivalent resistance at the emitter of the Q1. And R pi 1 is for the Q1 plus 1, like this, right? And then you just swap the RE by this value, RO2. Right? So, so I'm a little bit maybe tired with this. Not here for now. So this slide is trying to say that if you basically the DC biases are important. So let's say you have the microphone, you want to amplify it, right? If you just directly connect the microphone to the input, basically it it may change the bias that you want because the microphone maybe has some impedance to the ground, so it may crop the bias you are trying to make for the transistor. You usually do not bias it like this. If it means that the microphone may draw some current, DC current, right? So in order to avoid that, it's better, for example, to add some capacitor to decouple the DC bias of this and do not burn this microphone by biasing. Mm. And then for the AC, this cap is short, so it still can amplify the AC. So I guess we stop here. Tomorrow we will continue more the different configs. Basically, we learned today how to calculate the impedances from the base, emitter, and collector, and the gain for the common emitter. And we will continue for different configs. So we try to get used to not writing too much of cable KCL for the electronics. Try to understand how to transfer the impedances if possible and make good assumption somewhere that is not necessary to assume that there is a big resistor or something. You can skip the R out, right? Or some of the assumptions it's possible to simplify reasonably. Yeah, okay. Yeah, let's close this session. We will continue tomorrow, inshallah. Thank you so much for attending.